Alright, so in this example, we're going to go over melting and boiling, how temperature doesn't necessarily change, but we're changing our state of matter. We're going to be looking at the heat of fusion and heat of vaporization. Here's our student Logan helping us with the jokes of the day.
What's the internal temperature of a tauntaun? Lukewarm. What's the coldest temperature in which a marching band can perform? To below zero.
So in previous videos, we looked at how if you change your temperature, it changes the amount of heat that is absorbed or released in a reaction. But what happens if you have a change of state of matter? There is no temperature difference. The temperature will be constant or the same throughout. The reason why is it takes energy to break up the bonds of your forces for molecules. So if I look at molecules here, and let's say that they're in a solid, the molecules will be vibrating back and forth, but they're not going to rearrange themselves, right? If I take a heat source and put a fire under it, it'll take some energy to break up the bonds of the molecules, and that energy will be part to break the bonds, but it doesn't actually change your temperature because you're still in the solid form. By changing from a solid to a liquid, you'll be increasing the energy. So if I'm looking for the total heat gained or lost, Q total, that'll be the heat from a solid plus the solid to a liquid state, then the change in temperature for a liquid plus liquid to gas, and then finally the Q of the gas if it goes up in temperature.
The heat required to change a solid to a liquid, which is the heat of fusion, is the heat required to convert solid at the melting point to liquid, which is for ice, it is 333 joules per gram. The heat that is required to change a liquid to a gas is the heat of vaporization, and the heat required to convert liquid at boiling point to gas. For water, it would be 2,256 joules per gram.
Now the reason why the heat of vaporization is so much bigger than the heat of fusion for water, if you already have ice and you're just breaking the bonds of ice to turn it into a liquid, not going to take that much energy. But if I want the water to boil and to get to past gravity and whatnot, it's going to take a lot more energy. Also, the gas particles are taking up the place of the container, while the volume also changes as well. That's why it takes a lot more energy.
Okay, so right here to right here is what it takes from ice to go from below zero all the way to where it can melt. This right here is the melting point. Right here is water heating all the way up into here. And this big line right here is water boiling into the gas, and then this is the gas phase.
Good. If you notice when the melting point in letter B, that's the heat of fusion, the amount of energy required is not that much. But if we're looking at the boiling point, the energy required is a lot more. Think about if you're boiling pasta and you want to boil a big pot of water, it takes a long time for that water to heat up fast enough. Then you can actually see the bubbles forming. That takes a long time, but then once you see a few bubbles form, it's relatively quick in order to get past that boiling point.
Does the temperature increase during melting? No, it does not, because the temperature requires energy and the heat is absorbed. So on straight lines, it does not increase. Number 2, is energy required for each phase change? Yes, because you're constantly giving energy to heat that substance up. Number 3, can both liquid and gas exist at the same temperature? Yes, during a boiling point, because they are at the same temperature.
And number 4, what must be changed? Your temperature or heat energy during these. Your heat energy constantly needs to be changing as you're going from a solid to a liquid to a gas. So that answer will be your heat energy. So if I'm looking at my equations for heat transfer, the MCAT, you might have heard this, is M delta T times Cp. M is your mass, delta T is your change in your temperature, the triangle means change in. The Cp is your specific heat depending on whatever substance you have. The MC delta P only occur in the diagonal lines. The other horizontal lines will be the mass times the heat of fusion, whatever that number is given. And then the vaporization will be mass times vaporization to turn from a liquid to a gas. When you're going from a really low temperature all the way to a really high temperature, you have to add the heat of fusions and heat of vaporizations. A common mistake students do is they'll only do MCAT, but then they're ignoring the heat required to melt it and boil it. Okay, here's a sample question. It says calculate the heat required to turn 20 grams of water from 50 degrees Celsius to 110 degrees Celsius. I give you the heat of fusion and heat of vaporization numbers. When you're doing a question like this, you want to be able to draw the temperature differences. So here I have my temperature and here I have my heat. If I'm starting at 50 degrees, by looking at the chart here, this is negative, let's say 30 to 0. Then you're going from 0 up to 100, and that'll be past 100. So here will be 110. Notice where you're starting. We're starting at 50, so we're starting around here. I won't even need to know my HF, because that's the heat of fusion. That'll go right there. So if I'm going from 50 to 110, I first have to go from 50 to 100. That'll be MCAT. Then you go vaporization, and then you go up to 110. So first you'll do MC delta T. The mass is 50, the C is 4.18. The change in temperature will be from 50 up to 100 or 50 more. That is step 1. So if you multiply all those out, you get 10,450. Next step we got to do is use the heat of vaporization to see the boiling point. That's just M times the HV. Your mass again is still 50. Your HV is 2256. You want to multiply those, and you get a big number, 112800. That's because the energy required to boil water is very big compared to the change in temperature. Finally, you want to do the boiling point. There will be MCAT again, MC delta T. So here your mass is 50. Specific heat for gas is 1.99, we'll just say 2. And then I'm going from 100 to 110, that's just 10 degrees. By figuring that all out, you get 1,000. That was step 3 right here. Then you just add up all the numbers to find the total heat required. When you add all of those up, you get 124,250 joules. Now it sounds like a lot of energy, which it is quite a bit, but remember a joule is a fairly small unit. Alright, so that's Mr. Kaminsky and Logan helping with the pre-AP Chem question on thermodynamics. Any other questions, leave a comment down below or just shoot me a message.